Cool. So let's get started. First of all, congratulations on finishing week 1. I know it was probably really tricky for some people getting used to Zoom and everything, and just a lot going on at home. So congratulations, you made it. We went through the survey results, and it looks like we probably overshot this assignment a little bit. Apologies for that. It looks like a little under half the people took longer than 3 hours, which is not what we're aiming for. So we'll try to trim the scope a bit for the second week's exercises so that it doesn't take so long. But we hope that it was helpful to you and that you got something out of it, and that you feel a little more comfortable with Rust. And of course, this is just week 1, and we're easing in, so don't feel concerned if things still feel a little confusing. In fact, I plotted a word cloud of the reflections, and the biggest thing you see is frustrating Rust assignment, which I thought was funny. Some good things here, definitely helpful, understand, but I think this is actually everyone's first experience with Rust. Like, everyone I talk to, when they start learning Rust, they're like, damn, it's so frustrating. And that's always the word that everyone uses. And I think it is. And we'll talk a little bit this lecture about why that's the case and why it's so frustrating, and maybe what we can do about it. Some general notes. If you ever need an extension on an assignment, just let us know. In the course info, we said that, at least for the weekly exercises, that there aren't any late days. And that's because we want people to generally be on top of the material. It makes lecture easier, and it makes your life easier if you don't fall behind. But also, this is supposed to be a chill class, an enjoyable class, and we want you to have fun with it. And we understand that there's always a lot of things going on. So, and also, sleep deprivation causes coronavirus. This is true facts. And so really, like, we would rather you not stay up and work on these assignments. And if you're staying up, just send us a message, and we would be happy to give you an extension. Also, there's a lot of really good discussion on Slack and a lot of good comments about Rust and about Rust features. And I think it can be a little intimidating to somebody who has never seen this before, never heard about a lot of these things before, to see all this and be like, holy crap, am I behind? Like, am I supposed to know all these things? And I just want to make the point that although we're teaching this class in Rust, it's not actually a Rust class. And you're like, Ryan, what? Like, that doesn't make any sense. The point of this class is to expose you to ideas that you can take with you. We want you to see the problems with C and C++. And Rust is really a response to those problems. People have been fed up over the last 3-4 decades with problems that keep coming up. And so this is one way that people are responding. It's really the first language, I would say, that has actually gotten traction as a viable C and C++ replacement. And so I think it's good for you to see how people are responding to those issues, and then also to experience firsthand what are the problems with the response to the problems. I'm not going to pretend that Rust is a panacea, that like everything's going to work out great, because Rust also has a lot of problems, and there are reasons why we haven't seen mass adoption in Rust just yet. And so it's good for you to experience firsthand some of the barriers that come up. So yeah, if you see, first of all, feel free to ask questions. We love to talk about this stuff with you. We just want to make sure that you feel comfortable and that you don't feel intimidated when there's a lot of like fancy terminology flying around, or like you see talk of advanced features on Stack Overflow or whatever. We don't expect you to be Rust programmers in this class. So hopefully that's helpful. Roadmap for today, we're going to recap some ownership stuff that Armin introduced on Thursday. We're going to show some concrete code examples so that you can see how ownership works, or more often than not doesn't work. And then we're going to introduce error handling in Rust, and Armin's going to show you a worked example on Thursday of like how all of this plays out in a live code demo. So let's get started with ownership in C, actually. We're going to take a pause on Rust and look at how you may actually understand some of the stuff that we're already talking about. So this is a comment from some C code. It's from a project called OpenVSwitch. And let me minimize these Zoom videos because it is blocking the screen. And so this comment says, get status of blah, 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 return 0, blah, blah, blah. And it stores an error string in star error p and returns positive error no value. The caller is responsible for freeing star error p with free. And you don't have to understand the context of this or like what it's talking about. The key here is this caller is responsible for freeing error p. This function is allocating some memory for this error string, and it's returning a pointer, and it's saying the caller is responsible for freeing that pointer. Really what's happening here is this function is returning ownership of some memory to the caller. And we're designating that ownership in a comment because C doesn't really have any compiler notions of ownership. But this is really ownership. This function owned some memory. Now it's giving ownership of that memory to the caller, and the caller is now responsible for freeing it. Here's an example of borrowing. And so this function takes some dictionary, this const AV dictionary val. It takes some dictionary inside of this void star object. And it says any old dictionary present is discarded and replaced with this const AV dictionary star. The caller still owns this val pointer and is responsible for freeing it. So this is really like an immutable borrow in Rust. We're kind of borrowing a reference here. We're using this pointer temporarily, but we're not taking ownership of it. We're just borrowing it. The caller still maintains ownership, and the caller is still responsible for freeing it. Whoever has ownership is responsible for freeing this memory. So that's an example of seeing the same kind of thing that we're seeing in Rust in C comments. Here's something a bit more complicated. So this isn't a simple case of, you have ownership, now I'm taking ownership. It's a little more complicated than that. It says, note, the boot sysfs lib will free the data passed in for the caller when all refs to the target K object have been released. Blah, 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 lots of big words. But what this is saying is that as this function, I'm taking ownership, but I'm actually going to immediately pass it on to what they call the boot sysfs lib, and the boot sysfs lib is going to be responsible for freeing this data. I'm not going to free it just yet. It's going to survive a little bit longer, but I'm going to take ownership from you, and I'm going to pass it on to this library to free that data once all the references have been released. To give you some context, this is actually pretty similar to what happens. This is inside of the Linux kernel, and this is similar to what happens when you deal with entries in the open file table or in the vnode table. It's maintaining a reference counter, and when the reference counter hits 0, it's saying that the library is going to free the data. So really, this library, which is this abstract notion, a lot of different functions, is kind of taking ownership of this data and is responsible for freeing it eventually. Ownership gets really complicated, and like managing memory in C gets really complicated because sometimes libraries will implement their own free functions. They'll return you a pointer to memory, but you can't free it using the free function. You need to free it using their own free function. And that could be because there's some extra cleanup required. And so their free function takes a pointer to a struct, and then it frees a lot of pointers inside of that struct and then frees the struct. So maybe there's like multiple allocations that you need to free. Sometimes libraries will implement their own memory allocators. If you've ever run sanity check under valgrind, like you do valgrind sanity check blah blah blah, you'll see tons and tons of memory errors, and that's because sanity check is a Python script, and the Python interpreter implements its own memory allocator. Valgrind doesn't know about that, so it freaks out. It's like, wow, there's lots of memory errors. Not actually. It's just that Python is using its own memory allocator, and so you need to use its own specific free function. So this comment is saying the caller owns the data and must free it with not free, but this other function when that data is no longer needed. This becomes very challenging in C. Fortunately, it's a bit easier in Rust because we just have the notion that the caller maintains ownership, and Rust already takes care of freeing the memory when the owner goes out of scope and when the owner is not needed anymore. Rust takes care of figuring out which destructor functions, drop functions, should be associated with which data, and it handles that for us. Here's another example. let's see, why did I have this in here? Oh yeah, here's another example of like a different free function being needed. And let me check my notes to see if there was anything else that I wanted to say about this. Oh yeah, so ownership is, and you're going to see this in Rust too. The biggest ownership problems happen when there are structs involved. Ownership is easier to reason about when you just have a variable and like ownership gets passed here, you're passing a reference here, blah, blah, blah. But when you have structs that can own or like have pointers to other pieces of memory, that's when ownership becomes very challenging in Rust and also in C. And this function is dealing with a struct that also has pointers to other memory. And this function frees the struct, but it doesn't free memory that is allocated elsewhere that the struct points to. And so you end up with these complicated problems in C where like you may think that you're freeing a data structure, but you're actually only freeing part of the data structure, and you really needed to call another function to clean up the other part of the data structure. Rust doesn't let you make those mistakes, but it is also frustrating because it forces you to figure out all the ownership issues up front. Here's another example of this, where this function ends with free. It's supposed to be freeing memory, but actually it only frees part of the memory, and some other function takes care of freeing the keys. So this like partitioning of memory management is pretty challenging in C, and it shows up in Rust as well. So ownership is very complicated. That's something that has come up in pretty much every survey response. Everyone said that ownership is confusing and it's hard to wrap your mind around. But that's not actually because ownership is challenging in Rust. It's because ownership as a concept is challenging. Ownership is challenging in general. It's very difficult in C. This is why we mess up so many times and have so many memory-related vulnerabilities in C. And because the compiler is forcing you to work out all your issues at compile time, such that you can't have any possibility of issues in the future, it's like going into a relationship with some baggage, and it's like, no, you need to fix everything now. We're not gonna like just trial run this and like see how things go and like let things fall apart in the future. You need to fix all your issues now. And the Rust compiler is kind of like that friend that makes life difficult for you, but is actually really good for you in the long run. There was some confusion last lecture also about the performance implications, like what is actually happening under the hood when you pass ownership of something or when you pass references. And there's a key distinction to make between what is happening at compile time and what is happening at runtime. So at compile time, Rust is very different from C because it has this ownership model and it forces you to like figure out all your ownership issues, blah, blah, blah. But at runtime, it's actually pretty much the same as C. So if you pass ownership, you're really just passing a pointer. It's like passing a pointer in C. Except that the compiler is doing some work for you and it will insert the appropriate free call for you. If you pass references, that's also just passing a pointer. So there's no performance downside, or there's no real performance difference between passing ownership and borrowing a reference and passing that reference. They're really the same post-compile. If you explicitly copy some memory, then of course the compiler will copy the memory for you. But hopefully this is helpful to get a sense of what the Rust compiler is actually doing on your behalf. Does this make sense to everyone so far? Thumbs up, thumbs down? We'll say thumbs up. Cool. Feel free to unmute yourself and interrupt if there are any questions at any point, since I'm going a little fast. All right, so I'm going to do a quick demo with some examples of Rust code. And for these examples, I want you to think about, will this code compile first? Some of it is valid Rust code, some is not. If it doesn't compile, how could we fix it? And if the equivalent C code or C++ code would compile, why is it not allowed in Rust? Like, what sorts of issues come up if we write that kind of code in C? So here's our first example. Hopefully this is big enough for you. Take a look at this code and think, will this compile thumbs up or thumbs down? And we'll volunteer. I'll give everyone just a few moments. And can I get a volunteer to unmute themselves and then say, will this compile, yes or no? Yeah. Yes, it is. Can you explain more? That's exactly right. We have an immutable variable here. It hasn't been declared with the mute keyword. So when we do this push string, which modifies the string, that's mutating the object, but we said it was immutable, so that should not be allowed, and the Rust compiler will complain. If you do Rust C, then you end up with like cannot borrow as mutable because it was declared immutable. Okay, so what if we add this mute keyword? Does this fix our issues? Anyone? Yes, so this is a very simple warm-up. If we declare this as mutable, then Rust has no problem letting us mutate this string. So cool. There's some discussion about like whether this would work in C and C++ and why not. I'm going to skip it for the sake of time, but I have some lecture notes up on the website if you want to check this out. Long story short, it works the way that it probably should work in C++. C has a very weird notion of const. And unless you declare the string a certain way, C will let you modify a const string, which is very weird and not good. So no points to C for this example. All right, let's move on to just a slightly more complicated example. Does this code work? Yes or no? Think about it for a few moments, and then I'll ask somebody new to volunteer. All right, what do you guys think? Yeah. Yeah, so this actually works fine. Rust C, exercise 2, and it compiles fine. And what's happening here is, so we declare this variable. When you declare a variable, you get ownership of it because it's yours. You declared it. And there's no ampersand here, so we're passing ownership of this variable to omnomnom. Omnomnom takes ownership of that variable. It prints, and then we're good. Like, that's it. There's nothing after this program. That's the end of the program, so nothing bad happens. What if we were to do this? And this is an example from Armin's lecture on Thursday. Yeah. That's exactly right. And I want to make sure that everybody understands this because this is a really crucial example to understand. We start with ownership. Then there's no ampersand here, so we're passing ownership to omnomnom. Omnomnom runs, and it actually like exits. This function returns while still holding ownership of this string. Because it's going away and it had ownership, Rust will free this string after this function finishes. Like at this point here, that's when that memory gets freed. And then we try to go back to main. We return to main after this line, and now we try to execute this line. And of course, this doesn't work because conceptually we no longer have ownership. Like we gave ownership away to omnomnom the first time. But concretely, it doesn't work because the memory's actually already been freed. Like that buffer doesn't exist anymore. And so it would be unsafe to call omnomnom a second time because that memory's been freed. And most people look at this example and they're like, oh my gosh, this is really frustrating. This is really annoying. Why is it? The error message. So if I run rustc, it says that we moved the value here. We passed ownership to omnomnom on this line, but we're still using we're still using s after that. And that's not allowed because we gave away ownership. So most people look at this and they're like, wow, that's really frustrating. Why does Rust prevent such a simple thing from working? And my answer to that is this looks simple only because it doesn't have any mallocs or frees inserted. Like if we look at this code in C, this is one way that you could have written the code, right? We allocate our string, call omnomnom, call omnomnom again. Omnomnom just does printf. This is the same thing, but we have a free inserted. You could have written the code this way, or you could have written it this way, or you could have written it this way. Oops, not this way. Or you could have written it this way. And of those 4 ways that you could have placed the frees, you either have no free, so it's a memory leak. You have a double free, which is a potential security vulnerability. You have a free and then a use after free, or this is the only proper way. So of those 4 ways, only one really works. And Rust is forcing you to be clear, like which way are you intending here? Where do you want the memory to be freed? And it's not going to let you be ambiguous, and it's not going to let you make any mistakes. It's not going to let you do a use after free or anything like that. It's forcing you to be clear about your intentions. And I think that's unintuitive when you start writing Rust because this may not be something that you think about, but I think you'll find that as you practice doing this, it actually makes you a better C programmer because ownership is something that you need to think about in C. It's very, very, very crucial that you get ownership right in C. Even more crucial because the compiler won't catch your mistakes. And that's really what Rust is trying to do here, is to try to get you to think about ownership and be clear about what you mean. Does this make sense to everyone? All right, so let's talk a little bit about references and about borrowing, and hopefully that we can, yeah. That's a really good question. And so this is how we would write the C code, right? We want S to be freed inside of main. And so really what we want is to retain ownership inside of main such that S is freed when main finishes, when this S goes out of scope. In order to do that, instead of passing ownership, we can pass references. So here we would change this such that omnomnom takes a reference to a string, and then we borrow a reference here. And this way, we're keeping the ownership of S inside of this scope, inside of this function. And it'll be freed at the end of this scope when S goes out of scope. And then we're just really passing a pointer to omnomnom so that it can be used inside of this function. Great question. Does this make sense to everyone? All right, so let's talk about references because you can also have a lot of confusion in references as well. What do y'all think about this code? Does this work? Why or why not? Anyone want to take a guess? That's a really good question. It kind of looks like we're taking S and we're transferring ownership of S into S1, which means that it's no longer in S, and so you can't use S again. That would be true if we didn't have these ampersands. If you don't have the ampersands, that means like you're taking S and you're moving it into S1. The ampersand means borrow a reference. So what this code is saying is take S, borrow a reference to S, and put that reference in S1. Borrow a reference to S again, and put that in S2, and then use S along with those references. Does this work? This is not actually super intuitive if you haven't written Rust before. Yeah, think about this in a C program. If you have a value that never changes, then or think about this in the Google Docs example. Like if you have a bunch of people that are looking over a Google Doc that never changes, you can't have any issues where the Google Doc changes when somebody's looking at it. Like the whole reason that we introduced this notion of borrowing references and immutable references and whatnot is because we wanted to avoid that. I forget what the term that we used last lecture was, but we wanted to avoid that issue where somebody's looking at the Google Doc and somebody makes a sneak change to it such that that person is confused about what that Google Doc is now. This came from that vector example where like we thought we had a pointer to something inside of the vector, but then somebody reallocated the vector underneath our feet, and now that pointer is invalid. That's the kind of issue that we want to avoid, but this doesn't have that issue because everything is constant here. Nothing changes. Because S is immutable and all these references are immutable, it's totally fine to have multiple references at the same time to something. And so this code works fine. And if we compile it, the compiler comes back happy with no errors. What if we were to do this? Would this code compile? Okay, so there's one reference here to immutable string, and we said that you can have at most one mutable reference to a string. So this checks out. Does anyone want to make a counter argument? That's exactly correct. Rust's model is you can either have one person modifying and nobody else doing anything at all, or you can have as many people as you want reading. But as soon as you have one mutable reference or like one usage of a mutable variable, you can't have any other outstanding references. So you say, okay, well, that's fine. Let's get rid of this. I'll remove S2. All right, now we have one mutable reference. Does this code work? Why not? Yes, exactly. S is actually declared immutable, again, by default. And here we're trying to take a mutable reference. If this were allowed, you would be able to modify the string using S1, even though we declared it as immutable. And that's probably not good. So, okay, well, what if we did this? Does this code compile? How come? Yeah, you don't have two mutable references, but you kind of have two mutable references in some sense, right? Like S is mutable, S1 is mutable. They both are pointing to the same thing. And so that kind of seems like a bad time, right? And you are correct. If we try compiling this, it says, hey, this code doesn't work. You've got two references trying to be used at the same time. So let me throw, before anyone asks another question, let me throw something confusing into this mix. What if we split up this print line? So we have two print line, and let's do S and S1. Does this work? How come? Exactly. When I first look at this, I say, hey, this should not be allowed because you have two mutable references. They're not both references, but you have two ways of mutating the string outstanding. And that should not be allowed. But the Rust compiler is actually really smart, and it'll look at this and say, but in between where you create S1 and the last time where you use S1, like in between the lifetime of S1, you're not using S. There's nothing in between these two lines where S gets used. And because S is not used between the first time you use S1 and the last time you use S1, we're going to treat this as okay. What's really happening here is you're taking S, you're borrowing a reference to S, you're using it for some stuff, and then the last time that you use it, you're kind of returning the reference back to the owner. And so after this line, we get S, that reference kind of returned back to S, and we can use S as if there are no outstanding references, which is the case here. Does this make sense to everyone? This is a little confusing, and it will definitely take practice to get used to. What is the question? Would it still work if you print S before S1? Great question. And if you want me to try anything live code, you can just jump in because I don't have the chat window open. So does this code work? Anyone want to guess? What's that? So this actually has less to do with borrowing and more to do with like a reference counting issue. Anyone else want to guess why? So for the sake of time, this doesn't work because we have a mutable reference to S, and then S itself is mutable as well, keep in mind. So we have a mutable reference to S, which is still alive because we're going to use it later down here. And then we try to use S. And in effect, this is basically having multiple like writers of a variable, multiple things changing a value in memory at the same time. Because you could change this string through S, or you could change it through S1 at the same time, and we want to forbid that in Rust. The compiler says, hey, you have this mutable reference here, it survives all the way down here, but while it's still alive, you're trying to use S. S1 is mutable, so this should not be allowed.
We also have like a mutable borrow occurring while we have an immutable borrow. So it's like you have like a writer and a reader at the same time. That's kind of what the compiler is saying right there, right?
Yeah, it's smart enough to know that even though S is declared mutable, you're using it as a mutable here, but that really doesn't matter because you have a mutable borrow here. Like somebody could be changing the string, and at the same time that the string is being changed, somebody is trying to read this like intermediate contents. Yeah. That's a good question. And Armin, feel free to jump in if you have a better understanding than I do. But I think Rust just looks at the way that you've declared the reference, and that is what the reference is going to be. Even though println isn't actually changing what's inside of this string, it says you have a mutable reference here. You're using that mutable reference, and so I'm going to treat that as a mutable borrow. Println, by the way, is not actually a function. It's what is called a macro in Rust, and we'll talk about what macros are and how they're used later on. So that's why we see this mutable borrow reference here, even though println isn't actually mutating anything. So in the interest of time, I want to make sure that we get to some of the later content. But if you have more questions about this, definitely ask in the chat, and Armin can answer, or feel free to ask on Slack, and we'll help you out there too. All right, so let's move on to error handling. I'm running a bit short on time, so we may not make it through all these examples, but I want to bring this up because it's really important to have some understanding of how Rust handles errors. It's very different from C and C++. So here's some code. It takes a packet from the network, and it does something with it. So this is kind of similar to the example that I showed on the first day, where we receive some packet, we allocate enough memory. This doesn't have a buffer overflow. We copy the packet data into the buffer, and then eventually we free the buffer. I want to make the argument that this code has a security vulnerability. Does anybody know what's wrong with this? Mm-hmm. Yeah, I think most implementations actually return you a pointer to a buffer of length 0. And so this actually ends up working fine in that case. But you're on the right track. There's something involving something else here. Sorry? Oh, yes. Yeah, you have to assert that it actually returns some kind of pointer. And why might it not return a pointer? Well, malloc, if malloc fails, and the only reason that malloc will fail is because it can't successfully acquire memory, like there's not enough memory left. If this length is really large, there's a very good chance that malloc will not be able to allocate that much memory. You just don't have that much memory on your system. And it will return a null pointer saying that the allocation failed. And we're not doing any error checking here. And so this code is going to happily chug along and use buff when buff is null, and you'll get a segfault. So this is what is called a denial of service attack. You're denying service. You're taking down a service, really, by exploiting some vulnerability like this. It's not as bad as remote code execution, which we saw from buffer overflows, but it's still considered a security vulnerability because you may have some service that you don't want to go down, some critical infrastructure. And there's two real problems here. The first problem is that we're using null as a substitute for a real value, such that it's possible to take this buff and like look at this code and think that that's a valid pointer. And the other issue is there's not really a great mechanism happening here to signal that something has gone wrong. So I think I'm only going to have time to go through this first one, and then Armin will pick up that second point in the next class. So null pointers have caused a lot of issues all over the place. I have this link here where there are 1,627 vulnerabilities that are related to null pointer dereferences. And most of them are just denial of service vulnerabilities, which is like still bad, but not quite that bad. But sometimes you also end up with remote code execution caused by null pointers. I don't think I included the link to that one, but there's a link in the lecture notes. And the inventor of nulls calls it his billion-dollar mistake because it is so small and like so seemingly innocuous, but has caused so much grief in software. So why are nulls so dangerous? Like what's problematic here? That's true. So part of it is like there are pretty significant consequences for misusing a null. It's like a pointer to invalid memory. That's true. Would it be better if it was a pointer to valid memory? Yeah, maybe it shouldn't be a pointer. It definitely would be worse if it was a pointer to valid memory because then instead of having denial of service, you can easily have remote code execution. So that would be bad. I think the real reason that nulls are so problematic is because they place a huge burden on the programmer to keep track of what can be null and what can't be null. Oftentimes in C, null gets passed as a parameter. You see this in waitPID. Where it's passed as like the second argument if you want to say, I'm not interested in getting more information about how this process terminated. And it's used all over the place. And then it's also returned as a value. And if you're implementing a function, you have to like look at all your parameters and keep track of what could be null here and make sure you do all the proper error checking. And if you're calling a function and getting a value back, you have to think, could this function return null? And if so, you have to make sure that you handle that appropriately. There's a lot of burden on the programmer to keep track of everything. And if this list is any evidence, we just can't do that successfully. So what should we do about it? Rust solves this issue by introducing a type called option. And option can either be some or it can be none. None is really the Rust equivalent of null. But the difference is instead of like having null and like valid values mixed together in one type and you're not sure which is which, it introduces this option type that makes it abundantly clear, hey, this value could be null. It could be none. So if you're trying to return an option, you do something like this. If you want to return a value, you return some, that value, and you put it inside of there. Otherwise, if you want to return null, you just return none. And option, this is option containing a string. So whatever you put inside of the sum has to match whatever type is declared as part of that option. And then if you get a null back, how can you actually deal with it? So feeling lucky returns an option. Option is kind of an object. It's actually an enum. And we'll talk about Rust enums a little bit later. But it kind of works like an object. Like you can call methods on it. And so we can say, is this option, is it none? Or you can also say like, I didn't put it in the slide, but you can say is some to see if you got back a valid value. You can also call this unwrap or function, which says if it returned some, unwrap or will give you whatever that value is. So like if this returned I'm feeling lucky, then message is going to be I'm feeling lucky. But if it returned none, then use this as the default value. So if this function returned none, then message is going to be not lucky. And then really like the most idiomatic way to handle this, and you'll see this a lot in Rust code, is to use what's called a match statement. The match keyword is kind of like switch in other programming languages. It's a lot more powerful than that, and I feel like I'm doing a disservice to Rust by explaining it like that, but I think that's the most concise way to understand this. You say, call I'm feeling lucky, take the return value, and there are two possibilities here. It's either some or it's none. So if it's some, then do this, and message is going to be whatever that option contains. Or if it's none, then do this. And you can run this code, and it will either print got message, whatever the message was, or no message returned. So this is really how Rust handles nulls, and it makes it abundantly clear like when you can have a potential null value. If you can't have a null value, then you just work as normal, and a lot of times that's the case. But if there is the potential to be null, this forces you to think about like, how am I going to handle this? The compiler won't let you get away with just passing that off and not worrying about it. Any quick questions about this? We'll talk about error handling at the beginning of Thursday. If you want to jump ahead, you can read through the lecture notes. That should be pretty comprehensive. But the essence is that Rust uses this thing called result, which is very similar to option. And if you want to get a head start on the assignment, which is going to come out today, you may want to take a look at this to make your life just a little bit easier. So hope that was helpful. We'll pick this up on Thursday, and thanks for coming.